Good day. My name is Natalia Kosheleva. I am scientific researcher in the Institute of Continuous Media Mechanics of Russian Academy of Science, and I would like to present you a work entitled Measurement of Strain and Temperature by Fiber Optic Sensors Embedded in Samples Obtained Using Additive Technology, which was done together with my colleagues Valery Matveenko and Grigory Serovaev. One of the new directions of research in the field of material science is related to development and preparation of smart materials. According to the classification of smart materials given in the book that is shown on the slide, they should include one or more of the following components: sensing elements, actuator system, and real-time information processing system. At present, smart construction shows the greatest prospects in various fields: aviation and space, automotive industry, the railway transport, medical application and procedural tools, sport goods for new generation, appliances. Fiber optic sensors are immune to electrical interference and under harsh conditions can offer certain advantages over the other sensors, sensitivity included. Also, fiber optic sensor can be easily integrated with the other equipment for remote monitoring and allowing observing structure during all stages of its manufacturing, design, testing, and operation. Nowadays, FOSS have a number of applications in different areas that are shown in the slide. The classification of fiber optic sensors are shown on the slide. In our research, we will pay attention on the point fiber optic sensors based on the Bragg ratings and distributed fiber optic sensors based on relay scattering. On the slide, the structural scheme of Bragg rating operation is presented. The interrogator generates and transmits through the optical fiber the optical signal, which is wide-band signal in the prescribed interval of wavelengths. This signal is partly reflected from the Bragg rating. The main part of the reflected optical signal has wavelength, which is the resonance wavelength of the reflected signal. The value of this wavelength is directly proportional to the effective refractive index and geometric length of the Bragg rating period. This dependence determines the possibility of registering the variations in the relative length of the period by analyzing the variations in the relative value of the resonant wavelength of the reflected spectrum. The form of reflected spectrum of fiber Bragg rating is presented on the slide. Also, it should be noted that fiber optic sensors can be multiplexing on the one optical fiber, so the several Bragg ratings can be located at one optical fiber. One of the issues in the strain measurement with the help of fiber optic sensors based on the Bragg rating is the calculation of the strain based on information from the sensor and its correspondence to the material strain. The known relation establishes the link between the physical quantities recorded by the sensor and the strain in the zone of the optical fiber with the Bragg rating. These relations have the unique solution under the condition of uniaxial stress state in the optical fiber. However, in the general case, for the optical fiber embedded into material, a complex stress state is realized. When the fiber optic sensor is embedded in the material or even connected in some way with the surface, the material, for example by gluing a complex stress state in the sensor as a result of interaction with material, will be realized. There will be strains that need to be defined to the basis of experimental information. The operational principle of the distributed fiber optic sensor based on the relay scattering are shown in the slide. This technique relies on frequency modulation. The inside light wave is quasi-continuous wave, whose frequency varies linearly with time. The Fourier transform of the backscattered signal corresponds to the temporal trace of the intensity of the backscattering. In this work, an Auber backscattering reflectometer by Luna Innovations was used to carry out distributed measurements. The 3D printer was used to create our samples with embedded optical fiber. It should be taken into account that during sample manufacturing the difficulties occurs, among them the low adhesion between optical fiber and hosted material. Also, it should be noted that this can lead to the measurement errors. The process of 3D printing with embedded optical fiber can be divided into three main stages. At first stage, printing is performed up to the location of the optical fiber. At the second stage, the printing is suspended, the optical fiber is laid and fastened. The last step is to resume the printing process before it is complete. There are various ways of placing the optical fiber during embedding. In our case, the special group was used for the fiber placement to improve adhesion between optical fiber and the material. To measure the temperature, it is proposed to use an optical fiber with a point or distributed force enclosed in a hollow Teflon tube. In order to exclude the effect of mechanical strain on the thermal force, the fixing of the optical fiber and the Teflon tube should be carried out on one side of the tube using an adhesive joint, as is shown in the figure. The temperature force equipped in this way can also be embedded in the material during the printing process and used both of temperature measurement and for temperature compensation of fiber optic strain sensors. An experimental demonstration of measuring strains and temperature using embedded fiber optic sensors was carried out on the example of samples in the form of a beam of equal resistance made by layer deposition of polyactide. Two samples were made with the same geometric dimensions and printing parameters from the same material. Point force based on the Bragg ratings were embedded in one of the samples. As a result, two optical fiber lines were embedded into the first sample, an optical line with polyamide and two Bragg ratings, which were used to measure strains, and the second optical line with one Bragg rating enclosed in a Teflon tube for temperature measurement. For the second sample, distributed force was embedded, divided in two sections. First section was sensitive to strain changes, and the second section was enclosed in a Teflon tube to eliminate mechanical stress and to measure temperature. In the process of manufacturing samples, the readings of the force were recorded. On the slide, the graph of strain changes are given, taking into account temperature compensation, measured by point force. The whole history of printing process itself and the time period after printing is presented. It should be noted that the main process of formation of technological strains begins after the end of the printing process, during the cooling of the sample, and reaches an asymptotic value 5.5 hours after the force embedment. No changes in the structure of the reflected signal spectrum was observed during embedding a point force based on the Bragg rating. Also, the graph of the temperature changes recorded by temperature force is presented at slide. Based on the readings of distributed fiber optic sensor of strain and temperature, the distribution surfaces of these parameters along the length of the sample in the time are constructed and shown in the figures. Distributed force recorded the behavior of the material similar to point force during printing and after its completion. This allows to know the significant unhomogeneity of distribution of strains and the slight unhomogeneity of the temperature distribution along the sample. On the next page, the sample in the form of a beam of equal resistance was loaded, and the strains were measured using both types of embedded force. The sample was orientated in such a way that the embedded force experienced compressive strains. Two levels of load are applied with a delay in time at each step of load. The difference between the experimentally measured values of strain by point force, distributed force, and numerical calculation by finite element method and three-dimensional formulation of the problem of theory of elasticity does not exceed 10%. The process of creating samples made by fused deposition modeling technology from thermoplastic material with embedded optical fiber lines with temperature and strain force is described. The obtained results demonstrate the operability and reliability of readings of point fiber optic sensor based on the Bragg gradients and distributed fiber optic sensor embedded in sample manufacturing using additive technologies. Thank you for your attention.